Welcome to AP Statistics. Today, we are focusing on Topic 3.12, which is all about setting up a hypothesis test for the difference between two population proportions. By the end of this session, you will be able to identify the appropriate testing method, define the parameters involved in a real-world context, and correctly state the null and alternative hypotheses. When we compare two groups, like the proportion of students who prefer T versus the proportion of adults who prefer T, we are looking at the difference between two population proportions, which we denote as p-pi1 and p2. The parameters for a hypothesis test should always reference the population parameters, the response variables, and the specific populations in context. When we want to determine if there is a significant difference between the proportions of two distinct populations, we use a specific statistical procedure. This method is known as the two-sample z-test for the difference between two population proportions. We use a z-test because, under certain conditions, the distribution of the difference between sample proportions follows a normal distribution. Imagine you are comparing the success rate of a new medication in Group A versus Group B. Since you have two separate groups and you are measuring a categorical yes or no outcome, this z-test is your go-to tool. Before we calculate anything, we must define our parameters. It is crucial to refer to the population, the response variable, and the context. For example, you shouldn't just say P1. You should say P1 is the true proportion of all high school seniors who own a car. Being specific ensures your hypothesis refers to the entire group of interest, not just your sample. Now that we know the method and how to define our parameters, let's talk about the claims we are testing. In a two-sample z-test, the null hypothesis, or H0, always represents a statement of no difference. Essentially, we start by assuming that the proportion in population 1 is exactly the same as the proportion in population 2. If there is no difference between them, subtracting them results in 0. The alternative hypothesis is what we suspect might actually be true. We have three choices here. A one-sided test is used if we believe one proportion is specifically larger or smaller than the other. If population 1 is smaller than population 2, the difference is less than 0. If it is larger, the difference is greater than 0. If we have no specific direction in mind and just want to know if they are different, we use the not equal to sign for a two-sided test. Always make sure your alternative hypothesis matches the question being asked in the problem. If the problem asks if Group A is more likely than Group B, you are looking for a one-sided greater than test. Let's look at a concrete example to practice setting this up. Suppose a researcher wants to know if the proportion of students who pass a math exam using an online textbook is different from the proportion of students who pass using a physical textbook. First, we define our parameters clearly. P1 is the true proportion of all students who would pass the exam using an online textbook. P2 is the true proportion of all students who would pass the exam using a physical textbook. Notice how we refer to all students and specify the proportion who would pass. This defines the population and the response variable in context. Now, let's write the hypotheses. The null hypothesis states that P1 equals P2. The alternative hypothesis is that P1 is not equal to P2. The null hypothesis states there is no difference between the textbook types. The alternative hypothesis uses the not equal to sign because the researcher simply asked if they were different, not if one was better than the other. Alternatively, you can write H0 as P1 minus P2 equals 0, and H as P1 minus P2 is not equal to 0. You can write these either way. They mean the exact same thing mathematically. Using the difference notation is often helpful when we start thinking about the sampling distribution. Before we can actually perform the calculations for our two-sample z-test, we have to make sure it is statistically valid to do so. We check three specific conditions: randomization, independence, and normality. First is the randomization condition. The data must be collected using two independent random samples, or the data must come from a randomized experiment where treatments were randomly assigned. If our samples aren't random, they might not represent the populations accurately, and our results could be biased. If it is an experiment, the random assignment helps us establish a cause and effect relationship later on. Second is the 10% condition, which is specifically for sampling without replacement. We need to ensure that each sample size, n1 and n2, is less than or equal to 10% of its respective population size. We check this to ensure that the observations within each sample are virtually independent. If we take too large a chunk of the population, the probability of picking the next person changes too much. However, if you are working with a randomized experiment rather than sampling from a large population, you can skip this 10% condition. This is a common point of confusion, so always check if you are looking at an observational study or an experiment. The third and final condition is the normality condition, often called the large counts condition. For a two-sample z-test for proportions, we need the sampling distribution of the difference to be approximately normal. Here is a visualization of that bell curve showing the distribution of p-1 minus p-2. To satisfy this, we need to see at least 10 expected successes and 10 expected failures in both groups. However, there is a special twist for hypothesis testing. Since our null hypothesis assumes the two proportions are actually the same, we don't use the individual sample proportions to check this condition. Instead, we use something called the pooled or combined proportion. Think of this as dumping both samples into one big bucket to get a single best estimate of the shared proportion. We then use this combined proportion p hat c to check our four counts. We check that n1 times p hat c, n1 times 1 minus p hat c, n2 times p hat c, and n2 times 1 minus p hat c are all at least 10. If all four of these values are 10 or greater, we can safely conclude that the sampling distribution of the difference between the proportions is approximately normal. This allows us to use the z-table and normal distribution calculations. Now, let's work through a full setup for a problem. Suppose we want to investigate if a new fertilizer increases the proportion of plants that bloom within 60 days compared to the current fertilizer. The scenario is as follows. With the current fertilizer, 80 out of 100 plants bloomed. With the new fertilizer, 92 out of 110 plants bloomed. First, identify the parameters. Let P1 be the true proportion of all plants that would bloom within 60 days using the new fertilizer. Let P2 be the true proportion of all plants that would bloom within 60 days using the current fertilizer. Next, state the hypotheses. Since we want to know if the new fertilizer increases the proportion, this is a one-sided test. The null hypothesis assumes the new fertilizer is no different than the current one. The alternative is that the new fertilizer's proportion is strictly greater. Now, let's justify the test by checking the conditions. For randomization, the problem should state that plants were randomly assigned to the two fertilizer groups. We will assume a randomized experiment was conducted here. Since it is an experiment, the 10% condition is not necessary. Finally, we check normality using the combined proportion. Let's calculate p hat c. We add the successes, 92 plus 80, and divide by the total plants, 110 plus 100. Now we check the four counts using this 0.819 value. For successes, we calculate n1 times p hat c and n2 times p hat c. Next, for expected failures, we use 1 minus p hat c, which is 0.181. We multiply this by n minus 1 and n2. Since all four counts are greater than or equal to 10, the normality condition is satisfied. We have successfully set up the test. One of the most common mistakes students make in AP statistics is confusing when to use the individual sample proportions versus the pooled proportion. When you are creating a confidence interval for the difference between two proportions, you use the individual proportions, p hat 1 and p hat 2, because you are not assuming anything is true about the population yet. You are just measuring the spread from your data. But in a hypothesis test, our entire logic is based on the assumption that the null hypothesis is true. Since the null hypothesis says that P1 and P2 are actually the same value, it only makes sense to combine our samples to get one single, stronger estimate of that shared proportion. If we assumed they were the same, but used different proportions to check the normality condition, our logic would be inconsistent. So, remember, for tests, we pool. For intervals, we keep them separate. Take a moment to look at your notes. If you were checking the large counts condition for a confidence interval, you would simply check if the observed successes and failures in each sample are at least 10. In a test, we check if the expected successes and failures, based on that combined rate, are at least 10. It's a subtle but vital distinction for the AP exam. Let's look at another example, this time an observational study. Suppose we want to see if the proportion of residents who support a new park is different in the north side of the city compared to the south side. Here is our data. For the north side, we have a sample of 150 with 60 supporters. For the south side, we have 200 residents with 100 supporters. Step 1 is to define our parameters. We define P sub 1 as the true proportion of all north side residents supporting the park, and P sub 2 for the south side. Step 2 is to state the hypotheses. Since the researcher asks if the proportions are different, we use a two-sided test. Step 3. Check the conditions. For the north side, we need a random sample of 150 residents. For the south side, a separate random sample of 200 residents. We must state that these two samples are independent of each other. Next is the 10% condition. We check if 150 is less than or equal to 10% of north side residents and if 200 is less than 10% for the south side. Assuming there are at least 1,500 residents on the north side and 2,000 on the south side, this condition is satisfied. Finally, we check the normality condition using the pooled proportion, P hat C. First, calculate the pooled proportion, P hat C. It is the total number of successes over the total sample size, which gives us approximately 0.457. Now, check the 4 expected counts. We multiply the sample sizes by the pooled proportion and its complement. Since all counts are greater than or equal to 10, the normality condition is met. We are officially ready to perform the two-sample z-test. We have covered the foundational steps for setting up a two-sample z-test for the difference between two population proportions. Let's recap to ensure you have met the learning objectives. First, you should now be able to identify that a two-sample z-test is the appropriate method when comparing categorical success rates across two independent groups. Second, remember that parameters must always be written as the true proportion of all and must include the context of the problem. This shows you are describing a population, not just a sample. Pooled proportion is only for the normality check in a test. Third, in your hypothesis statements, the null hypothesis always assumes no difference, which we can write as P minus 1 equals P2. The alternative hypothesis depends on the specific question asked in the prompt. Finally, you must justify your test by checking the 3 conditions. Use the combined or pooled proportion for the normality check to stay consistent with the assumption that the null hypothesis is true. Think about a scenario in your own school. If you wanted to compare the proportion of freshmen who play sports to the proportion of seniors who play sports, what would your null and alternative hypotheses look like? Taking the time to set up these components correctly is half the battle in statistics. In the next topic, we will use this setup to actually calculate the test statistic and the p-value to reach a conclusion.